Now we'll be discussing backbone networks using some concepts we first described in Chapter 6. That was the chapter on network design. Backbone networks are high-speed networks that connect other networks together. That's LANs, WANs, and VLANs, which we'll soon learn about. The distribution layer, that's backbone networks connecting access LANs. And the core layer, which is backbone networks connecting different buildings together. So those are the different types of backbone networks and how they're all set up. Thank you. All right, now we're going to discuss backbone network components. They consist of the network cabling. In faster data rates, they use fiber if they want to have a strong backbone. And as far as switches, they have the transparent layer 2 switches, which operate at layer 2 on the OSI model pretty much. They are truly switches. They don't have IP addresses. They have management features associated with them, but they're not layer 3 switches or VLAN switches, which are going to be somewhat of a new concept that we're going to go into a little bit more detail. They're devices that combine the features of layer 2, and they have some routing features that they also handle. And they're used in VLANs, which is why they're called VLAN switches or layer 3 switches. Thank you. Now we're going to talk about the various components, starting with routers. Routers are network layer devices that connect different networks. They're also TCP/IP gateways. So if you ever look at an IPv4 configuration, the router is going to be the gateway in that configuration. Routers are not transparent devices, which means they are very visible. Messages passed up to the network layer, including the network layer, are stripped off into. Let me try that again. Messages are passed up to the network layer, including stripping off data link layer frames. So as the messages are passed up, the encapsulation is being handled, like we discussed, and routers respond to ARP requests, which is the Address Resolution Protocol, and it determines what needs to be done based on that. It reads IP addresses, and it will determine the best route, and routing requires more processing than switches because it's working with the MAC addresses and the IP addresses. Thank you. So you may be wondering right now, is there really that much difference between a layer 3 switch or a VLAN switch and a router? They both receive IP addresses in VLAN. It's our assigned IPs and subnets. So it seems like there's a lot of similarity there. They both forward on the basis of IPs, like I just said. And layer 3 switches are faster, so why not always go with them? Well, layer 3 switches or VLAN switches usually do not support WAN connections and only Ethernet for LANs. Usually they only support TCP/IP, and there's many other differences as well. Thank you. So now let's talk about routers. Routers forward each packet independently. They ignore previous IP packets to the same destination. They make a full router forwarding decision. They take a great deal of time to make these decisions, and this makes routers slow and also inexpensive. And routers adjust rapidly to failures. Thank you. Layer 3 switches are almost the opposite of routers in some respects. They do not forward each packet independently. They do remember previous decisions based on IP. And since they don't need to make a full router forwarding decision, it requires much less processing time, making a layer 3 switch or a VLAN switch fast and inexpensive. However, these considerations do make failure recovery slow and difficult. Thank you. And one more thing I should mention. Usually the connectors between a layer 3 switch and a router are different. A lot of times if you're connecting from a backbone to a router to a local area network, the switch or the VLAN switch will likely have RJ45 Ethernet connections, and that's going to be your only way to connect to it. Whereas a router will have the connectivity for the various backbone cabling and what have you. So routers are bigger and routers are more powerful, but they can be slower and they require much more processing time. Thanks. Now let's talk about VLANs and virtual LANs, which really occur with VLAN switches or layer 3 switches. Routers segment networks based on physical location, i.e. the cables that are connected to it. Remember, router cabling and interfaces are much more complex usually than switch interfaces. Switches are usually limited to an RJ45 connection, and I did say usually, not always. Devices in different physical locations may need access to the same LAN resources, so it's quite frequently necessary to have something print in a business office or something like that. I know that you can send a printout to the registrar's office pretty much any time at Albertus if necessary for a student's report or some information. Anything can be sent to their printer if they have the proper authorization. So that's an example. VLANs perform flexible LAN segmentation so that it can be based on logical instead of physical design. So when you're dealing with LAN segmentation, it's very, very easy to draw a simple logical diagram of how the network will be without having an actual physical layout of each machine. Once the LAN is segmented, it's quite simple to simply call that part done and focus on the backbone and the main layers. VLANs are enabled by high-speed layer 3 switches or VLAN switches. They're much more complex to manage and typically only used in large networks. Like I said, at a university or something like that, you might have a student VLAN, you might have a faculty VLAN, you might have a staff VLAN, or it might be broken down by department, but typically that's how colleges are set up. So certain information, whether it be a multicast message or whatever, is manageable. Thank you.
Welcome to Virtual Local Area Networks, or VLANs. This presentation is designed to introduce the topics of VLANs and VLAN trunks and give an example of how the technology is applied in a networking situation. Proper implementation of VLAN technology leads to broadcast containment, network organization, and a level of network security. A VLAN allows a network administrator to create logical groups of network devices that act as if they are on their own independent network, even if they share a common infrastructure with other VLANs. What does this mean? It means that a networker can logically configure a single physical switch to act as if it is multiple and separate logical switches. Moreover, multiple switches that are configured with similar VLANs can be interconnected, and devices on the same VLAN can communicate with each other across those switches. A simple VLAN implementation is displayed in this diagram. There are two groups of users in this graphic, faculty and student. Notice that when all PCs are under the same IP network, and PC1 sends a broadcast, all devices receive and must process that broadcast. One benefit of VLAN implementation is broadcast containment. Each VLAN is its own broadcast domain. After VLAN implementation, broadcasts sent by PC1, which is now on VLAN 10, only reach other devices that are on VLAN 10. No longer do devices on the student or any other VLAN receive or process broadcasts from the faculty VLAN. Broadcast containment is beneficial because it reduces unnecessary network bandwidth usage due to broadcasts. As a result, the amount of CPU cycles devices use to process the broadcasts is also reduced. When VLANs are implemented, each VLAN must be on a different IP subnet than other VLANs. Because of this, a Layer 3 device, such as a router, is needed to enable communication between VLANs. This inter-VLAN routing is beyond the scope of this presentation. Another benefit of VLANs is network organization. Think about a school, for example. It makes sense for there to be 3 VLANs, a student VLAN, a faculty VLAN, and perhaps a guest VLAN for visitors that may need internet access. This is shown here. Notice that each VLAN has its own subnet address. Another example of a VLAN implementation might be an enterprise headquarters building. In such a building, there may be many departments such as research and development, management, shipping and receiving, accounting, advertising, and human resources. Assigning each department to its own VLAN leads not only to broadcast containment, but also better network organization. Because different VLANs require different IP subnet addresses, a layer of security is also provided by VLAN implementation. In our example of a school, the student VLAN is separate from the faculty and guest VLANs. This logical separation reduces the probability of confidential information such as grades, student information, and other administrative information from being compromised. Access control lists can be used to further enhance security across VLANs. Now that you know some benefits of VLAN implementation, let's look at the most popular type of VLAN configuration, static port-based VLAN assignment. Static VLAN assignment requires an administrator to manually assign each port on a switch to a specific VLAN. As you can see here, specific ports have been assigned to specific VLANs. Generally, the administrator will create the VLAN first and then assign the ports to the appropriate VLAN. The device that is plugged into the port automatically becomes part of that VLAN. If someone in an organization moves from an office on one floor to a different floor, a simple port configuration enables that person to continue to participate in the appropriate VLAN. VLAN switches are often connected by using a crossover cable. These switch interconnections are called trunks. Trunks carry traffic from all VLANs on a single cable. Without trunks, each VLAN on a switch would need its own cable to connect to its matching VLAN on another switch. Trunk ports solve this problem by tagging frames with specific VLAN information. The most used tagging protocol is IEEE 802.1q. In this animation, when switch 2 receives the frames, it tags them with the VLAN information from which they originated, 10 and 30. After traversing the trunk lines and arriving at switch 3, the tags are stripped and the frames are sent out the appropriate ports to arrive at the correct end device. This concludes our video on the benefits and operation of VLANs. Implementation of VLANs is extremely important and common in large LAN environments. Although the information in this presentation is important, it is only introductory. For more information on VLANs, go to www.cisco.com and search for inter-VLAN routing, VLAN configuration.
Okay, that was our CCNA presentation. Thank you very much. In this slide, we'll discuss the advantages and disadvantages associated with virtual LANs. There's much more flexible subnetting. There's a better managed traffic flow, which may lead to faster performance. And you're able to prioritize traffic, saying this traffic here is more important than this traffic here based on the subnet it comes from. The disadvantages are that it's complex and there's much more management and responsibility involved with VLANs, especially when VLAN memberships change. In other words, when somebody moves from one VLAN to another. Layer 3 switches are definitely more costly than Layer 2 switches, as Layer 3 switches actually do exist in Layer 2, but they kind of do functions that exist within Layer 3, so that's kind of a gray area as to what a Layer 3 switch is and where it sits in the OSI model. But layer switches, since they are programmable and configurable, are much more expensive than a standard Layer 2 switch. Thank you. Now, before we get into the backbone network layers, I want to go over a few quick things. You'll notice I made this slide extremely colorful, and I wanted to get your attention. It looks like the 4th of July here, but let's go over it. Before we discuss the backbone network layers, I want to make it really, really clear that these layers are not the same thing as the layers in the internet or the OSI models. These are sections of the backbone networks, and they're referred to as different hierarchical layers. They're not the same thing as the OSI model or the internet model, so please don't confuse the two. These hierarchical layers include the access layer, the distribution layer, and the core layer. We went over this in some detail in Chapter 6, and I highlighted that at the bottom. So this slide here is colorful, and it's your warnings, and it's your basic information. Thank you. And they're largely based on the devices used. There's switched backbones, there's routed backbones, and there's VLANs. In practice, it's common for an organization to use a combination of all the architectures because growth occurs sporadically, and a lot of times management won't be prepared for it, and a lot of times it needs to be kept up and running, and answers need to be expedited. So it's not uncommon to see a combination of many different architectures. Thank you. The type of backbone network used in the distribution layer, which we've discussed above. And it uses layer 2 switches, and the switches come from different form factors. They're the desktop, the rack mounted, and the chassis. These switched backbone networks, since they are switches, they go with the star topology and the physical location of devices. Most commonly, they have closets in the back of a room, or a switch closet. It's more common to locate centrally in the main distribution facility, or like I said, a wiring closet. So that's usually how the devices are set up. Thank you. Routed backbone networks are sometimes referred to as subnetted backbones or hierarchical backbones. They're usually used to tie buildings together or other large campus type situations. Sometimes they do exist at the distribution layer, however. Advantages include LAN segmentation, and disadvantages include that they tend to be slower. Routing is slower than switching. More expensive. Routing is more expensive than switching. And harder to manage. Thank you. This is a diagram of a typical routed backbone architecture. Notice where the routers are placed and where the different switches at the different layers are placed. Thank you. Now we're going to go through the best practices. When considering architecture, it's important to remember that switched backbone networks have the best cost to performance ratio at the distribution layer. Most organizations use routed at the core layer, and VLANs are becoming more widely used, especially for organizations needing flexibility, because that programming at the switch is right there for you. The technologies considerations: gigabit Ethernet for the distribution layer, gigabit Ethernet or faster at the core layer, and always have redundant devices and connections, and drives for that matter too. Thank you. In a perfect situation, the best practice network design would look like this. where the core network would be routed or VLAN switched to a layer 2 or a VLAN switch, which would exist at the distribution layer, and it would then go to the access layer with perfect symmetry and perfect balance for each building. However, that's not the real world, and this is what we strive for, but often we upgrade buildings at different times when different technologies exist. No department has the exact same number of people in it, so you have to balance your resources. There's so many external factors that get in the way that the best practice network design is not very often a reality. This is something we shoot for. This isn't something we often achieve, although it has been achieved before. And if you're a new company and you're just getting set up, you don't exist yet. So it's important to try and come up with a good plan that meets your current needs, but yet considers your future expandability as well. Thanks.